Hey student, I got a question here from a number, let's see, what is the number? This number 14. And so number 14, and I guess this is chapter 39, and it's on our relativity here. And so let's give it a go here. It says two identical twins. And so we got Speedo moving fast and slow, or go slow. And they're joining a migration from planet Earth. So I'm going to make a little E here for Earth to planet X. Okay, so they're moving from here to here. And it is 20 light years away. Now let me pause right there. All of these questions need to be followed up, or all the information need to be followed up with relative to what? You know, because lengths are all relative. And so how far is it relative to whom? You know, how much time elapsed for whom? You know, what is the force as measured by whom? What is the momentum or kinetic energy as measured by whom? And so it says in reference frame to both planets that are at rest. Okay, so if somebody was measuring it, and then let's just say that I'm over here, I'll put me over here at planet X, and I'm going to put you, the student, over here at the Earth. And then we're going to make two spaceships. And maybe I'll put an S here for Speedo and a G for go slow. Because when they say it is 20 light years, we have to say as measured by whom. And so they gave that very clear. It's 20 light years away in the reference frame in which both planets are at rest. Now, the twins are of the same age, and they depart at the same moment, but on different spacecraft. Now, Speedo's spacecraft travels at 95% the speed of light, but Go Slow only travels 3/4 of the speed of light. Calculate the age difference between the twins after Go Slow's finally lands on planet X. And then, of course, which one is older. So you can see what's going to happen here is Speedo's going to get here first. And then eventually Go Slow. And then we're all going to get together. Me, Speedo, and Go Slow. And maybe we'll even say, for the sake of discussion, that I'm actually the same age as the twins, at least when they leave. But because they have relative motion between each other and myself, the rate at which they age is all different. And so we want to keep track of all of those, and that's what's going to make this kind of an interesting problem. But keep in mind also, when we go to compare their age, we're all going to be on planet X. And so we should then, probably have the ultimate question of, how much has age as seen by, this person here on planet X. See, because planet X is going to be me, and as I look at Speedo and Go Slow, their clock is going to dilate, right? Remember what we said, moving clocks run slow. So these will slow down. So both of these twins will be younger than me. Of course, that's not really the question. The question is which one is younger, because there is something that kind of tricky here that happens. Your first reaction is, well, Speedo's going to be the younger one because the clock's going to go at a slower rate. And that's true while they're traveling. But you see, Speedo's going to get there, and Speedo's then is going to get onto planet X with me, and we're just going to hang out for a while waiting for Go Slow to get there. At which point, Speedo is going to look back at Go Slow and say, well, now your clock is running slow. So definitely by the time Speedo gets to me on planet X, I would have said, well, okay, Speedo is younger than Go Slow. But then Speedo is going to be aging at the same rate I am, which is slower than Go Slow. And so maybe, Speedo in a sense catches back up. And maybe Go Slow is actually younger. Just kind of looking at the numbers, I don't think that's going to happen. But it could happen. And that's why it's kind of impossible, without going through a bunch of mathematics here, to figure out which one is going to be at a little younger age here. So let's do this. Probably the easier one to do is go slow, because go slow just has the motion and that's it, whereas Speedo has some motion and then sits on planet X for a while waiting for go slow. So what I'll do is I will say a couple of things, like how much time elapses for me as I'm waiting for go slow to get to me. And so I'm going to use the kinematic equation that you learned in Physics 121. Maybe I'll just write it as distance equals velocity by time. Maybe you remember it as some initial position, some initial velocity plus 1/2 at squared. But for this problem, go slow is not going to be accelerating, just traveling at a constant speed. And we'll just say they start at planet Earth at x equals to 0. And so if you place that with a distance and that with a v, you get t. And so these are kind of one and the same equation. In fact, I'm going to write it then as t equals distance divided by velocity. So the distance that go slow travels from my perspective. So I need to put in the distance from my perspective and then the speed of my perspective, and that'll give me the time from my perspective. So I'll give all of these from my reference frame. And so the distance is 20 light years. I'm going to write it, though, this way. I'm going to write it as a time of 20 years traveling at the speed of light. So that's what we mean by 20 light years. How fast would light travel in 20 years? Now, I know I could look this up in meters and convert all this to meters, but I think I'm just going to make that harder on myself, because if I take the time in years and then multiply by c, watch what happens from the speed. Now, go slow is going 75 c. And that way, c's will cancel off, and I never really need to look up the speed of light in any units. So I don't need to worry about meters or kilometers or any other. And I don't really need to worry about the time. We could, in other words, we could have thought of this as so much per years. And so that way, whatever units they are, they cancel off. And so we're just going to get 20 divided by 0.75 with the unit of years. And so this will tell me how long it'll appear from me. And kind of makes sense that it's, above 20 years. Looks like it is 26.67 years. So here is go slow. So keep in mind, from my perspective, as I wait here on planet X, I'm going to have 26 birthdays, and then I'm about 2/3 to my 27th birthday from the time they left. So like if I was 20 when they left, I'm looking now, I'm 46.6 by the time go slow gets here. Now, if I extend this to say, okay, now looking at go slow, I may go, okay, how much time elapsed for go slow? And you could say that go slow's time dilated by a factor of gamma, if you will. And so everything biologically has slowed down. And that's probably the easiest way to do it. I guess you could also do kind of like I did here. You could say the time experienced by go slow would be the distance experienced by go slow divided by the speed of go slow. And either one should get you the same number. Oops, probably shouldn't put gamma here. I should probably put time dilated by gamma. There we go. And so how much time really, occurred here. Maybe I could, write it as you saw it in class. Delta t equals to gamma delta t proper. Now, proper, of course, this is where we got to be careful. This is kind of my warning to you. Proper means there's no motion. So I'm holding a clock in my hand here, right? And I'm going to say, how much time elapsed on my clock, and that'll be this proper time, whereas the time for go slow is a non-proper time. Well, let me figure out this gamma factor, and so it's 1 over the square root of 1 minus 0.75 squared. And so 1 minus 0.75 squared, taking the square root of that, and then the reciprocal of that, it looks like about a 1.51. And as long as I'm doing some math over here, why don't I get the gamma factor for speedo? I have a feeling, even though we're not talking about speedo quite yet, I'm going to need that also. And so I'll go 1 minus 0.95 squared. Take the square root of that. Take the reciprocal of that. It looks like 3.20. And so this gamma factor was the one that we kept talking about. It comes into play in terms of length contraction and time dilation and any of our Lorentz transformations. All right, so back to this problem. So this problem then would say that go slow clock, you know, from my perspective, and then ultimately that's where we're going to have go slow. Go slow is going to be on planet X. So this clock that is sitting on planet X has been reduced by this factor of 1.15. I think I wrote it wrong. Yeah, 26 years. Okay. So if I take the 26.67 years and divide it by 1.51, we're looking at about 17.67 years. So again, just kind of keeping track, go slow is going to only have 17 birthdays. And then they're 2/3 on to 18th birthday. And so when I, you know, the clock on planet X, meet up with go slow is younger than me. And so maybe I'll just say here, younger than me. By whatever this difference is, this 26 2/3 minus the 17 2/3. I guess I didn't need a calculator for that. So 9 years. So 9 years younger than me by the time go slow gets to me. Okay. Now, what about speedo? Oh, I guess I kind of started saying here, maybe I'll do the same thing. I could have done this from the perspective of go slow. I could have said go slow's perspective would have said that the distance, instead of being 20 light years, has been contracted by a gamma factor. And that distance to the planet X is still traveling that way, or I guess from go slow's perspective, they would see planet X approaching go slow at this rate. So there's a shorter distance at the same speed, which is why the time works out. And if you'll notice, that's kind of the same number because we really took the time and divided it by gamma, and we got the time by taking 20 divided by this 0.75. And so we should get the same thing. Why don't I just give it a try? So 20 light years divided by gamma, 1.51, and whatever we get, we're going to divide that by 0.75, and sure enough, we get 17 2/3. So no matter how you want to look at it, and we have kind of two ways we can look at go slow, we're going to see that go slow is going to age 9 years less than me. So when they get together, like I said, it was pretty obvious at the beginning that go slow is going to be younger. Now we got a number to work with. Go slow is actually 9 years younger than me. Let's look at now speedo. So speedo, we can kind of do the same logic. We can say that speedo is going to take a certain amount of time to get to me. And from my perspective, and I'll just kind of do that same thing, distance divided by velocity. From my perspective, I'm going to say speedo is traveling 20 light years, which I'm going to write as 20 years multiplied by c. So I'm kind of doing the same thing that I did right here, the time and the speed of light. And so it's 20 light years. But of course, it's 0.95 c. And this is, like I said, kind of a convenient way of using the units. The c's cancel off, and so I get 20 divided by 0.95. And we're looking at about 21.05 years before speedo would get to me. Now, clearly then, that 21 years, is less time than the 26, right? So this is how long go slow is going to take me. So in other words, after I've waited around for 21 years before somebody gets here, which speedo gets there first, so I've waited for 21 years for them to get there, speedo and I are going to hang out together on planet X until go slow gets there. And so we've got some more time, and the difference between this 26.67 years and the 21 years is how much time we have to hang out. Not sure if I should do that calculation first. I'll hold off on that one, because as long as I was in this groove here, like we did for go slow, I could figure out how much time is on my clock, but I could also figure out now how much older is speedo. And so speedo would look like this. We would take this time, this 21.05 years, while I was waiting for speedo to get there, and I can divide that by the gamma factor for speedo. And so during this traveling, speedo only has 6.58 birthdays. I think it rounds to an 8. Yeah. So you can see a lot of time dilation here. In other words, speedo's only thought of it as 6 years to get to there. Of course, I thought it was 21. So again, notice that speedo is a lot younger than me. And you can even see a lot younger than 9 years. So clearly, speedo is ultimately going to be younger, although by how much, let's see, because keep in mind that although speedo's aged 6.58 years as speedo was traveling towards me, now speedo has to hang out with me for a certain number of years, and that would be this 26.67 minus the 21.05, because go slow's not going to get here until my 26.67th birthday. So this is a 2, this is a 6, this is a 5. So me and speedo are going to hang out for another 5 years. So the total of these two, how much did speedo age while they were traveling to planet X, plus the number of years they hang out together. And so I'll add these two together. The 8 and the 2 make a 10. Carry 1. The 5, 6 make a 12. Carry a 1. And then that makes a 11, 12. And so they've aged a total of 12.2 years. Or not they, well, speedo and anybody in that same spaceship by the time we add this, which is the time that go slow gets here. Okay, so if I got this right, speedo has aged a total of 12.2 years. And Go Slow has aged a total of, what do we say, 17.67 years. And then myself, which I don't think really is relevant to the question, is 26.67 years. So Go Slow has aged more than Speedo. So Speedo's younger than Go Slow. And they're both younger than me. Now I got to go back to the question. What was it? Calculate the age difference between the twins. All right, so finally, to finish the problem, I subtract the 2. 7 minus 0 is a 7. 6 minus 2 is a 4. And 7 minus 2 is a 5. And so 5.47 years is their age difference. Yay! All right. Hope that was helpful. Take care.